current is coming out from the battery, from the negative side obviously, stops right here and branches into R3, current that goes through R3, and currents that goes through R4. Then goes here, stops and branches into I6 basically, and the current that goes through the R8 and R9. So this makes us understand that resistors 8 and 9 are in series because they are crossed by the same current. You always start from the end to shrink your circuit. So this is what the circuit looks like once you put those two resistors 8 and 7 in series. You add those values and you have the total value of 7. Then the rest is just recopied. So don't pay attention to those numbers yet, because those numbers I solved afterward. Right now we are just shrinking the circuit and calculating the equivalent resistance. Then you go to the next one. In this one, what you see is that resistors R6 and resistor 7 are both of them in parallel. So you do the 1 over 1 over to calculate the equivalent resistance 6, 8, and 7 for a value of, because this is 7, this is 1, this is 0 point, so it's smaller than the value, the smallest value there, so that's right. So you can be sure that what you're doing fine. And then at this point what you have are those resistors all in series because crossed all by the same current, so you can go ahead and add them up. So when you add them up, you find at this point the same circuit copied, R3 is still in place, but instead of having 1, 2, 3, and 4 resistors, you have one unique one, which is the sum of those. Then at this point you notice that this resistor and this one, okay, they are in parallel. So again, you go at this point over here, okay, you calculate the parallel between those two resistors, the 3 and this number here, okay. Then you calculate the parallel of this, and you go through one more step, and you put together, you leave R1 and R2 in place, and substitute those two with just the parallel, okay, of those two resistors. And then finally you solve for the last one, which includes only the last series, okay, and contains only the equivalent resistance, which is 8.908 ohms. Now guys, if you round too much, it can be challenging. So at least I kept 3 decimals. Okay, so once I reach this point, I calculate the equivalent current, which is 2.25, and now I start my way back. Okay, so let's see if this method makes more sense to you. Once I have everything calculated for this resistor, I can go back to the previous step. For this step, I know the current that was going through the system, right? So because of this current, I can calculate the drop in voltage across every single one of those resistors. So basically what this means is that once I have the equivalent resistance, I have the equivalent current, then I see from the picture, okay, from the last picture, I see that R1 and R2 are crossed by 225, so I go ahead and I put 225 on top here. Okay, once those two currents are in place, I can calculate the drop of voltages across V1 and V2. Now, how is this important? Well, once I have this drop here, I can do the 20 minus this value to calculate the value across this branch here. Okay, so this will tell me the voltage across this big resistor here. Now, where did I get this resistor from? So let's go backward again. So I got this from the parallel between those two resistors. So if I know the resistance, if I know the voltage across are 3, 9, 6, 7, and 8, basically this means that this resistance is the parallel between those two, right? So if I know this voltage across this resistor, then I know that those two are coming, this resistor here is coming from this two parallel. So this means that both of those have the voltage of 1.95. Or you can go all the way back and you can calculate the drop across R1. Yeah, right. So once you have your voltage of 2.20, once you have the amps of 225, you can put it across as current that is going across R1 and R2. At this point you can calculate voltage across V1 and V2. Now what are those two values? Those two values are, for example, at the beginning of your circuit. So this is your V1, this is your V2 over here. Okay, so at this point you can calculate the voltage across R3. Okay, and make sure that you go back to the picture that you need for that particular calculation. So R3, okay, we have the voltage across it. So we go back to the table, okay, and V3 is this, because we calculated as a 20 minus this number, so 125 you have, R3 you have, so you can calculate I3. I3 is 1.95. So 1.95 is here, here, everywhere I have R3, I can go down and I can put 1.95. Now if I do that, I also see, for example, from this picture here, okay, I see also that I started with 225, I'm losing 1.95, I have 0.197 amps across this resistor here. But this resistor, where did I get it from? Well, I got it from here, right? So this means the 0.197 is the current that is going across every single one of those resistors. So in particular is going across R9, R4, and R5. So I can go back and I can say R9, R4, and R5 are all the green current. Okay, according to that I calculate the voltage. Okay, once I have those voltages, what do? Again, I go and I put it in the picture that I need, in particular, for example, here, right? So I have drop, I have drop, I have drop. So at this point I can calculate this voltage here as a 1.95, because 1.95 was the voltage that I had across R3. I'm losing this number, I'm losing this, I'm losing this. So I am left off with 0.177 volts across this resistor that is 6, 8, and 7. Now where do I get this? Where did I get this resistor from? Go back one space. So this was the parallel between R6 and R8 and 7. So this also means that because I just said those are parallel, 0.177 is across R6 and is also across R7, 8. So for 177, I put it in the table as a V6 right here, okay, and I can calculate how much current is going through it, right? So this is the current across, and then at this point I need basically the 7 and 8. 7 and 8, I can see that I was coming in with the 0.197 amps. I'm losing 0.177 amps, so I am left off with 0.017 as an amps. Those amps are going through this resistance here, which is the series of those two. So now I can solve also for those drops if I want to. Okay, so drop here and drop here, because I'm putting this value in the table. So because I'm putting those values now, those values, according to, if I am calculating those by subtracting this current from this current, or if I am calculating those directly because I calculated the voltages, I mean, there are roundings that are always, it's hard even for two persons to have exactly the same number. But as long as you have a 0.02 or something like that, where you see this 0.017, or if you have 0.2 or something like that across those resistors, so for those values, you're fine also. So those are the this is the solution for the circuit 1. Then we can do together the circuit 2. Circuit 2 is coming from, which one was it? So this is the circuit 2. Okay, so let's go ahead and let's work this one together. So all my colored pens. Okay, so let's start shrinking the circuit. So first of all, okay, we are starting from here. Okay, so current is going across R1, R2, R3. Now starts branching. So this one branches into R4, and so N goes here, okay, and then becomes some here, some here, some here, and some here, here, and here. Then those two join and becomes red again, and then those two join and become green again, and then those two join and becomes purplish again. Okay, so those are all the values that we have. Now at this point, let's start shrinking the circuit. Okay, so those are the values. We don't need those yet. Okay, let's start shrinking. So let's start with the battery there. So we're starting from here. Let's start shrinking from the back. So here you have the first R1, R2, R3, R4, R6 I have here, R5 is there, and then R7, and then those two are crossed by the same current, so R8 and R9 are in series. So this is the R8, 9. It has a value of 5 because I got to add those two. 5 ohms. Then what happens with those values? So I see that I have, again, I can follow the current there. So I have the current that is going here, stops here. Then I have the black current. Then I have the green here and here. I have the orange. I got the other black here across R7. This is red. And then here I have the last one, which was the blue. So I'm noticing that those two resistors are now in parallel, right? Because they are not crossed by the same current. So they are in parallel. I can solve now for the new parallel. To be honest, I can see also, well, let's do one step at a time. So here this and this. 4, 6, 5, and then here I will substitute the parallel of the R7, 8, and 9. Okay, so this is 1, 2, 3, 4, 5, R6. So this value here is the parallel between this and 7. 7 has a value of 6 ohms. Okay, so for this one I do 1 over 6 and 1 over 5 over, right? So 6 over plus 5 over, enter, over. So 2.73 is this value. Okay, so once I have this value, I go across again. Okay, and let's see, we have this current going across, coming back here. Then I have the black one here, and then green and green, orange and red. Okay, so this current here, those two, this current and this current, the orange and red are different, so this means that those two resistors are in parallel. So again, I can do one more step here. So this is R1, R2, R3, R4, R5 is right here, can't touch it yet, and then this one instead, right, becomes the parallel between those two. So this is R6, 7, 8, and 9. So again, this is the parallel between those. R6 has a value of 3. Okay, so now we can do 2.73 over plus 3 over, enter, over, and this is 1.43 ohms. So again, one more turn. So let's go around and back. This is the current black, and this is the green that now is going across every single one of those resistors. So those two are in series then, which means that if I draw the circuit again, as you do those drawings for the circuit, keep in mind which ones are those resistors in series, in parallel, what are those properties in particular. So then once you have the equivalent resistance and the equivalent current, you can go fast between those values and finish solving. So let's put together those two values that are in series. So R5, what is it? R5 is 2. Okay, so this is resistance 5, 6, 7, 8, and 9. So those are in series, so we add them up. So this is going to be 3.43 ohms. Now we have the parallel between those, and then the last one is going to be the series. So this is R1, R2, R3, battery, and this is your R4, 5, 6, 7, 8, and 9, which has a voltage of, so R4 is equal to 1. Yeah, 1 ohm. Well, that's it. So 1 over, obviously, plus 3.43 over, enter, over, and this is 0.774. 10.774 ohms, and then we can add everything together and find finally the equivalent resistance as the series of those. So the equivalent resistance, which is equal to, so R1 is 5, so this is 5, R2 is 4, R3 is 1, so adding those is 10, so this is 10.774. Our equivalent is equal to 10.774 ohms. Okay, so the voltage was 18, so this is 18 volts. So from here we can calculate the current. So 18 divided by 10.774, and you have a 1.67. So the purple current is 1.67 amps. So I can go all the way on top and put this one as a 1.67. Technically I can put it everywhere I see the current coming out from the battery. Okay, so here I didn't do it, but that was the one. So 1.67. Okay, and then let's finish this one off. Okay, so now at this point what can we do? So we got to work with the table also at the same time. So we found the our equivalent as 10.774 ohms, and we found the I equivalent equal to 1.67 amps. And using those pictures, we went all the way to put the 1.67 across R1, so I1, and across R2, so this is I2, 1.67 amps, so 1, 2, and 3. So I3 is also 1.67 amps. And now I gotta stop right there because this is the only purple current I got. So here I can calculate those voltages. Okay, so 1.67 times 5 times 4, okay, whatever. Times 4, I did this one first, so 6 point, so this is B2, 6.68 volts, and then so 1.67 times 5, so this is 8.35, V1 8.35, and then V3 is just this multiplication, so V3 is equal to 1.67 volts. So this is awesome because I got drop here, drop here, and drop here, which means knowing that this was 18 volts, I can calculate the drop here. Okay, so by doing 18 minus 8.35 minus 6.68 and minus 1.67, I got a 1.30. So 1.30 is this. 1.30 volts is the drop across R4. Okay, so I go here and I write V4 equal to 1.30 volts, which means I can calculate also the current across it. By dividing those two values, I have I4 equal to 1.30 amps. Now I'm here. So all done up to this point. So I can also keep on writing also the values that I find, is those are easy ways, right? So I was also here, whatever you want to write it. So this is 1.30, we said, and the current we just calculated is, what did I just say? Oh yeah, those were the same. So this is 1.30 amps also, we calculated from here. Okay, then this current was 1.67, minus 1.30, I have a 0.07. So this current looks like a 0.07. Okay, so let's keep on following the flow of current. Okay, what else can I calculate? So here, this will be also 0.07, and I also have a drop here. So for R5, I have a I5 of 0.07. Okay, or let's see what other alternatives do we have. Okay, so for example, in this picture here, let's see if you like this one also better. This is 1.3. So I'm losing all of this current, right? So 1.67, I'm losing 1.3. So this is also the 0.0, the 0.37. What else? So this is 0.37, and I can mark it everywhere there. 0.37, 0.37 here, and this one will give us a drop of voltage of 0.7. So 0.74. So V5 is 0.74 volts. 5. So this is the drop that I have right here. Okay, so this means is also the drop that I have here due to the current, like we were saying, 0.37, which is the same drop that I have here. So basically I can now calculate. So this drop here was 1.3. So this voltage at this point across R4 is 1.3. I'm losing 0.74 volts. So how much is the voltage across here? So the orange one. Well, so 1.3 minus 0.74, and we have a 0.56. So voltage here is 0.56, which means is also here 0.56, which is also here 0.56. V6 equal 0.56 volts. So this means 0.56 divided by 3 is giving us so I6 equal to 0.187 amps. So here there's a 0.187 amps. So I had 0.37. I'm losing this. How much current is the red one? So 0.37 minus 0.187. I have a 0.183, which is the current with which I'm coming here, which is also this current is 0.183. But in particular, so being this the current that is going in this branch, okay, so here this current is splitting into this and this, which is also meaning that is the same red current, which is this one. So 0.183 is going across this resistance here, which is 7, 8, and 9. 7, 8, and 9. So this means I can calculate the voltage across this resistance here, right? But this resistance and this resistance are in parallel, so this voltage here is also 0.56. Now what do we do with this? So 0.56 is the voltage across this parallel, which by being a parallel has the same voltage as across R7 and across R8 and 9. So this voltage is also 0.56, and this is also 0.56. So this means that the current that is going through R7 is equal to, so 0.56 is the voltage, divided by R7, which is 6, is equal to 0.0933. R6, oh, R7, so I7 and V7. So V7 is 0.56, which makes sense because all of those resistors are all in parallel. We could have seen that since before, but we can do step by step also. So it's normal that all of those resistors have exactly the same potential. So the current here we said is equal to 0.0933 amps. So finally we have R7 and R8, which are actually in series, so crossed by the same current, which is so this is 0.0, I can keep on writing it here, 933. So we are coming with 0.183. We are losing 0.0933, and we have a 0.0. So this is going to be 0.0897. 0.0897. So those currents are the same, I8 and I9, 0.0897, 0.0897, which means that the voltage V8 and V9 are equal to the product between those two, so 2 times 0.0897 is 0.179 volts, and this instead is 3 times 0.0897, which is 0.269 volts.